Hi, in this video I want to take some time to explain zone settings and window settings in detail. To get started, we begin with the workflow template selection, and I want to use the simple shoebox model setup as a basis to explain these parameters. So in detail, what we want to talk about is these settings. So if you click on these settings, we're presented with a series of tabs and settings that define internal gains that happen in the zone, that the HVAC system that is conditioning the zone, some ventilation settings that can model airflow in the zone and hot water demand in the zone, as well as the constructions that wrap around form the envelope of the zone. And finally, there's some settings such as fuel conversion factors and CO2 conversion factors that we can talk about. So let's begin with with the zone settings. You also okay, so let's go through these settings one by one. The first two parameters are really only there to help you organize your thermal model, where you can specify a name or a description for the zone used case or type. And then you can also use a drop-down menu to kind of classify the use type in this zone. Second, we have a people section where we can specify the number of people within a space. In this case, we do this by with a people density value given in people per meter squared. And we can also specify a metabolic rate, an occupancy schedule, and an airspeed schedule. So what does this all mean? So from people within a space, we can expect a significant heat gain. Humans emit heat, and depending on their activity, this can change. So as you see here, the heat rates that are emitted from people or students that are engaging in different activities are different, and you can kind of look these values up in the ASHRAE Handbook of Fundamentals. So based on that, we specify a people density, we specify a metabolic rate, and then we have we can compute the heat gain from people within a space. As you see down below, there's a schedule, and these schedules are used to modulate these parameters. So this is the maximum, if you will, the maximum people density within a space, or the maximum occupancy within a space, and then this is modulated with a schedule. And schedules really can be looked up from manuals or standards. And in this case, we are citing the SIA reference with the Swiss architectural norm, the 2024. And here you can nicely see the assumptions that go into these schedules. For example, for an occupancy schedule bedroom, we see there's an occupancy of 100%, and then this is falling down to kind of 40% occupancy in the morning time. Then there's increased occupancy around noon or 1 p.m. and then this is falling again and then ramping up at night. And in the office scenario, this is almost opposite, where you have no occupancy during the nighttime, and then this is ramping up in the morning and dipping down again at lunchtime. And these schedules are used to modulate this maximum people density. If we go back, we find in the next segment here this equipment power density that we can specify, and this is similar to the people. From equipment emits heat in spaces as well, so we can specify the wattage per meter squared that we have installed in a zone. And just to kind of give an example again, if you look at electric appliances, there's different wattages kind of specified here that are typical. Just to kind of pull out the computer example, if you're looking at a laptop, then you can expect something around 80 watts per equipment, and close to 300 watts if you're using a desktop computer. So there's a significant difference in heat output. If you kind of planning a space, you need to take this into consideration. Down below we find the lighting. The lighting is again, similar. It's a heat gain, but it's modulated or modeled differently, because for lighting we can specify an availability schedule similarly to these above, but we also can dim the lighting if we have a dimming system, and we can specify a targeted luminance. And if this can be met with daylighting, then a dimming system such as continuous dimming, for example, can modulate or scale down the lighting system as well, in addition to this availability schedule. In the next tab we have the HVAC system components that condition the zone. First of all, there's a set point that can be specified, and there's two modes. There's a constant set point mode where you can just specify a constant temperature in Celsius, or you can schedule it to modulate the set point temperature over time, and this allows you to do the typical kind of setbacks. Again, there's an availability schedule. This is for the entire system. So if you want to specify that the heating system can only run in the winter, then you would select a schedule here that would only allow the system to operate in the winter. In this case, it's turned on always, and we're kind of relying on these set points to control when it turns on and when it's turning off. You can also specify limits. And this limit is interesting if you want to modulate real systems that have a limited heat output capacity or a limited flow rate. In this case, we want to focus on ideal load scenario. We want to calculate the heating and cooling loads in this space, so we run this with kind of this imaginary system that doesn't have any limits. To explain this a bit further, we can look at the slides again, and typically you would have a thermostat within a space that you set to a certain temperature. And now you may have two different thermostats for heating and cooling, and if you're doing this kind of energy modeling, it's really important that you specify a so-called dead band between the heating set point and the cooling set point. And this should be around 4 to 6 degrees C or K in this case, so that these two systems don't start fighting each other. Especially if you do not specify these availability schedules accordingly. So in this case, we have 20 degrees C here and 26 degrees C here, which is a good setting, a good starting point. We can also do humidity control, where the system can dehumidify the air or humidify the air, and this by default is turned off, but you can turn it on and then set kind of a minimum and a maximum range here for the humidity ratios. And then lastly, there's a mechanical ventilation segment where you can specify the minimum amount of fresh air in liters per second per person and in liters per second per zone area. Again, there's an availability schedule and a bunch of other parameters that we will talk about in a minute. So for these fresh air settings, if your building is mechanically ventilated, there are norms or standards and regulations that specify minimum ventilation rates. And these are usually specified per person, and this is modulated depending on the occupancy that we had specified in the other tab. So if there's no one in the space, this ventilation rate goes down. If there's full occupancy, then this ventilation rate goes up. And you basically specify a value here for the maximum occupancy or full occupancy. And just to kind of, again, look at this more specifically, if we look at these ventilation rates, there are, again, this is taken from the ASHRAE Ventilation for Acceptable Indoor Air Quality Guide. In table 6.1, you see different ventilation rates specified. For example, if you're looking at an educational facility, a daycare, you see a 5 liters per second per person value specified and 0.9 liters per second per square meter. Okay, now let's talk a bit more about the system. You notice that I skipped over the COPs further at the top. For cooling, you can specify a COP, and for heating. And we also did not talk about the heat recovery option and the economizer options here yet. So for the COP, really, we use this COP to model efficiencies. And what is the COP? It's kind of the thermal energy that needs to be provided in the space, divided by the electric work that needs to be put in. So the COP is often referred to when we talk about, for example, electrical heat pumps that we can use for heating and cooling. And a typical COP here is ranging from 2.7 to 3.5, depending on the type of equipment that you use and the temperature source that is kind of used to elevate or pump the heat. So for example, if you have an air-based system, this is a typical value. If you have a ground-coupled system, this value can be higher. This can be up to 5. If you're using a typical gas furnace, you can, in a similar fashion, use the COP. Although we do refer to the efficiency here. We usually talk about the efficiency, and this ranges from 0.7 to some value close to 1 if you have a condensing boiler. Also, we can specify heat recovery systems. This is basically modeling an idealized cross-flow heat exchanger, for example, or I can also model an enthalpy wheel depending on what you select. So if you go back to these settings, the way you can start using a heat recovery system, and this again, the heat recovery system refers to this mechanical ventilation flow rate. You can set this to sensible, then we would be talking about a cross-flow heat exchanger, or you can set it to an enthalpy wheel, which can also recover some of the kind of dehumidification or humidification aspects of the outdoor air that you bring into the zone. You can specify a sensible recovery ratio and a latent recovery ratio, and this is usually around 60%. Also, you can use an economizer if you want to basically just use increase this ventilation rate during the summertime to remove some cooling load. If you're using an economizer, it's recommended that you actually start limiting the system, especially the flow rate. Otherwise, you might end up with unrealistic flow rates in the zone, because the system will try to use outdoor air to cool the interior without any conditioning happening. Lastly, if you know a bit more about your system, then you can specify a fan power rise, and you can. This is basically then modeling a simple fan energy using an ideal fan model. And of course, what is this referring to? If you're looking at a system, ventilation system with ductwork, all of these ducts obviously add resistance to the airflow. If we add a cross-flow heat exchanger up here, there's an additional resistance that this adds to the whole system. And this resistance needs to be overcome by a fan to circulate the air within a space. So this is what we would then specify here under the fan pressure rise, and this is a delta in pascals. So let's move on to the ventilation tab. Here we can specify scheduled air changes with the outdoors. This is can be used to model natural ventilation, for example. There's a set point control for that, and then a schedule that we can use to modulate the magnitude that we can specify in this kind of hourly air change. This is handy if you know these flow rates already, if you're using a different tool like COMIS, or if you have a CFD simulation that gives you this data, then this can be very useful. Otherwise, there's other simpler modeling. Otherwise, you can use different models to model natural ventilation. As you see here, there's this simple airflow modeling objects that can model buoyancy-driven flow and wind-driven flow, and will not go over these in detail as of now. There'll be a separate section talking about natural ventilation. What I want to talk about is this infiltration rate down here. So infiltration rates obviously are kind of like an unwanted natural ventilation that is occurring in buildings because they're never fully airtight. And again, you know, there's wind forces that act on the envelope that cause infiltration, but also internal kind of heat gains that cause a stack effect within a zone, and that draw in air more at the bottom and then squeeze out air at the top. And for airtight, more modern buildings, this typical air exchange rate is 0.2 to 3. For more leaky, older buildings, this can go up to 1 to 2. And see that, as you see here, there's a box where you can basically specify the air change rate for the infiltration, and then there are some parameters that you can use to model this air exchange rate differently. The default is always just a constant term, which basically will just module a constant air change rate of 0.5 throughout the year. If you want this value to fluctuate with outdoor temperature or wind velocity that's changing in your weather file, then you can use these parameters to influence this air change rate. If you want to know more about this and what parameters you should set, you can always look it up in the Energy Plus input-output reference, where there's good default values specified here. The Energy Plus default is always using this constant term, so this is what we also recommend moving forward. In the hot water tab, you specify a peak flow rate and a supply temperature and a mains temperature. So this is the water temperature that you want to have for the hot water, 60 degrees in this case. And then there's a mains temperature specified. This is kind of basically the temperature of the water as it comes from the municipality, and this would be at 10 degrees. You can specify a schedule, and again you can specify a COP for your hot water demand, similarly to the heating and cooling COPs that were specified earlier. And then let's move to the next tab, which is the constructions tab. So here we specify constructions for roof, facade, partition, slab, and external floor. You can also specify additional internal mass by specifying an exposed surface area in meters squared per zone area, and then again assign a construction to it. Looking at constructions, obviously what we are kind of aiming for is we basically build up these constructions out of multiple layers of different materials, and you can do this in ClimateStudio and Grasshopper using these kind of layer components and a construction component to layer them all the way up. If you want to be code compliant, for example, this is pulling out New York City, which is in climate zone 4, R values or maximum U values in this column that you can follow if you want to be code compliant. And just to compare this to different climate zones, this is changing obviously if we are moving, for example, to Ithaca, which is in climate zone 6A. We have much more stringent U values specified here for the constructions. To change these settings here, you can, if you hover over this, you get the U value information and heat capacity information that you need to know to select constructions accordingly. And if you click on this, you're presented with an selection interface that can pull different kinds of constructions from a library, and there's a couple of them specified here that may be of interest, but you can obviously also create your own constructions just by clicking on this plus icon. It will ask you to provide a custom name, and then will basically duplicate the construction that you had selected, and then if you scroll all the way down to the one that I just created, and then you can start editing it by adding additional layers and so forth, and commit with OK. So these constructions are specified for these typical objects such as roof, facade, partition, slab, and external floor. These are auto-detected in the networker component for you, so you don't have to worry about figuring out which construction goes onto which surface. And lastly, I want to talk about these carbon and cost factors. So here we see heating fuel CO2 emission factors given in kilograms per kilowatt hour and heating fuel cost factors given in dollars per kilowatt hour, and so forth. Now, you can get, these are good assumptions for electricity, kind of for the US national average, but these are obviously dependent on the utility that provides the heating fuel to you and what kind of fuel you use if you don't use electricity. A good source for these conversion factors is always the power profiler by the EPA, and you can just kind of navigate to that website, type in your zip code, and we'll give you at least the CO2 conversion factors, although in different units. Okay, and lastly I want to talk about the Windows settings. So if you click on the settings button here, you're presented again with a dialog that allows you to specify a couple of things. So first of all, you can switch the window type between internal and external. For this kind of setup, obviously we want to use an external window, but if you want to model internal windows as well, you can basically indicate that here. And you have to basically make this pre-selection, separate the internal windows from the external windows beforehand, and then you specify whether the set that you're modifying here should be internal or external. Then you can specify a glazing system, and again, if you kind of refer back to our slides, you can go to these and use these ASHRAE 90.1 specifications, where you see there's a given U value for fenestration and solar heat gain coefficient specified as well. If you go down one more slide, we see some typical values for glazing systems. So if you're talking about a single pane glass, we have a U value of around 6, the solar heat gain coefficient very close to 1, and the visible transmittance is similar. As we add more layers, we get better U values, better solar heat gain coefficients, and depending on in what kind of climate we're building, we want to select combinations of U value and solar heat gain coefficients that make sense. So if we want to have high solar gains to offset some of our heating loads, we want to pick a glass that has a high solar heat gain coefficient and a low U value to retain the heat. If we want to block out solar gains, then obviously we want to pick a glass that has a low solar heat gain coefficient, and usually it matters on which layer we have a low E coating. This is something to watch out for. So specifying these parameters is really difficult, and that's why you probably better off using using objects that come from a library. In ClimateStudio, we have implemented an extremely large set of glazing systems that are coming from the International Glazing Database. So it's basically combinations of glazing paints, actual glazing paints from actual manufacturers, so that you can select and choose them from a fairly large list, as you can see here. So you can sort by U value, you can sort by solar heat gain coefficient, and then pick a glazing system that makes sense for your climate and for your purposes. If you can flick through them here. Then you can specify a frame and a frame conductance and a frame width, which basically then automatically draws a frame around your window and then models the heat loss and heat gain through this frame for you. Further down, we have a shading system that we can specify. So this is basically modulating a dynamic shading system for you. It's kind of like this, as shown here in the slide, without specifying this geometry. So it's a dynamic system that can be turned on. It can be exterior or interior. and it can be controlled or triggered through different control types. So for the first one here is on. If high solar on window, this means basically if there's a lot of radiation falling onto your window surface, this system is triggered and lowered. And to let the program know when this should happen, you have to also specify a set point. And the set point is either in watts per meter squared, if this is a radiation-based control, or if you have a temperature-based control, such as high outdoor air temperature, then the set point would be in Celsius. And then finally you can specify a transmittance value of this shading system. So this is basically how translucent is your, if it's fully opaque, this goes to 0. If it's if it's just a mesh or a screen, then this would have to be a different number. Down below there's ventilation settings that are relevant if you're doing airflow network simulations that can be assigned to these windows, and then finally some zone mixing parameters that are only relevant if you have internal windows. So we'll skip over those and talk about them in a different tutorial. So with that, we have basically explained in detail the settings for the zones and settings for windows that make up the thermal model, and by changing through them, you'll see kind of the effect of these parameters on the full results.